because some terms sound so similar. Oh, I know. A meteoroid, that's like a space rock. A meteor is the streak if it falls through the Earth's atmosphere. So meteors are like meteor shower. It's like woof, very fast. And the meteorite is if anything makes it through the Earth's atmosphere, you pick it up. I hate it. Meteoroid, meteor, meteorite. Do those sound alike to you? Yes. So in science, there are definitely these kind of clusters of terms that sound alike. This is an example of a term that you're like, I know what that is. Okay. So let's see what it is. Standard. Do you remember when we been talking about H's, mean it's enthalpy, and we said if you have an H that has a little, and I call that knot, that's my K-N-O-T, that means standard conditions. Okay? So what, that's 25 degrees Celsius, 1 bar. And I double checked, and 1 bar pressure, that's equal P. 25 degrees Celsius is equal to your T. 25 Celsius, by the way, is 77 Fahrenheit. I looked it up, I Googled it today. And a bar in terms of pressure is almost 1 atmosphere. So we're under the influence of about 1 atmosphere. If you climb a mountain, your pressure goes down. Yeah, you get less pressure. You know, if you go underwater, your pressure increases. So that's the standard part of it. Enthalpy, well, that must be the H. So there you go. Standard enthalpy. Okay. Mole formation. So I would say formation of 1 mole. So basically, it looks like this. We're going to see that these are chemical reactions. They are formation of 1 mole of something. Okay, and we are going to do the delta H of this reaction, and actually we're going to call it delta H sub F, means the standard molar enthalpy of formation. Okay, and we're going to build it from its elements. So these circles are the reactants, these are elements. And we're going to make, this is a compound, CPD for compound. So standard molar enthalpy of formation. I don't know if that helps, but it just seems, it screams like that makes sense. Standard 1 mole molar enthalpy delta H formation, forming 1 mole of a compound. Anyway, so in so many words, this is it. So a minute ago, I put kind of a chemical reaction from elements to form a compound, and we know we've been talking about enthalpies of reactions, delta H's of RXN. So standard molar enthalpy formation is the energy change accompanying the formation of 1 mole of anything, okay, from its elements. Now, I need to kind of talk about this. The elements aren't just elements, but the elements need to be in their standard states at standard conditions. So standard states are liquid, gas, solid, okay, AQ in some cases, I think. I don't know if that'll work. Wouldn't work for elements, but works for something else. Standard conditions, I just told you. You're talking about 77 Fahrenheit, about 1 atmosphere, which is 1 bar. Okay, that's the little knot part of it. So if you're like, I don't know what an element is in its standard state, what its standard condition is in standard state, well, just think 77 Fahrenheit and 1 atmosphere pressure. What's it going to be? Okay. So, you saw me a minute ago, for kind of that, I was just putting the elements, goes to form a compound. So if that is the formation of 1 mole of compound from elements that are in their standard state, then the heat of that reaction, the delta H RXN, is really a heat of the formation, delta H sub F. It's a special heat of reaction. It's the heat of formation of that compound. Standard state. Yeah, I said that's the solid, liquid, gas, you know, whatever it's going to be. So for instance, you're like, look at the periodic table. So these are things we're going to be joining together in standard molar enthalpies of formation. Most of these are solids, quite frankly. A handful are gases. Okay. Standard conditions, I already told you. To me, that standard conditions, and it's different from standard conditions for gas law problems. But this is the knot. That's the little superscript. K-N-O-T. It's thermodynamic standard conditions. All right. Well, here's a little thing to kind of put back as a tool for you. If you have, and you'll be using this to your benefit. What are you dressed up as, Benny?
I'm the hippie version of Michael Jackson.
Oh, yeah. The hippie version of Michael Jackson. It's like, that's not usually what she wears. You'll have to get up and do something.
Yeah, I did it in the main office. I had to.
Oh, good for that. Good for you. Okay. So if you have something that is in it's an element. If you have something that's an element, okay, and it happens to be in its standard state. Remember, all what I mean by standard state is solid, liquid, gas. Okay, at standard conditions. Then its heat of formation, or delta H sub F naught, is 0. It's like a baseline. That might, I'll show you. That will kind of come in helpful. We'll see some examples of that. So I'm going to show you the three. Was it last Monday, a couple days ago, we talked about Hess's law, and we kind of took 3 puzzle pieces to come up with the combustion of benzene. Benzene is your C6H6. I'm going to show you those 3 puzzle pieces again. I'm going to show you that actually those equations represented the standard molar enthalpies of formation. So here's what I mean. See, there's my compound. There's benzene, CPD, and there's the element hydrogen. There's the element carbon. I just need 6 carbons and 3 H2s to get the whole thing. So actually, this guy right here it's a special heat of reaction. It is actually, bless you, the standard molar enthalpy of formation of C6H6. It just is. Okay? Because the equation that it represents is the standard molar enthalpy, or the equation it represents is the formation of one mole compound from elements in their standard state, their standard conditions. This one too, check it out. Now we're going to look at some examples on the next slide. Do these reactions represent the formation of 1 mole of compound from the elements in their standard states? And if they do, like these do, then their heats of reaction, there's also heat of formation of the compound that's formed. This is, look, 1 mole of CO2 formed from, and we talked about the allotropes of carbon. Remember, we have diamond, graphite, which is the standard state for carbon. We have buckyballs, and then we have the graphene, the nanotubes. Okay, so yeah, and then this is the last one. So these were our puzzle pieces. Again, the formation of 1 mole of compound from elements that are in their standard states. The state is indicated by the thing in parentheses, the formation of 1 mole of compound. So all of these are heats of formation. Sometimes I just like drawing. So we're going to look at some, I think there's maybe 5, and I think we'll go around the room. I'll put you each on the spot. So I'll show you one. I think you guys love that. We haven't done that for a while. I'm going to show you one, and then you get a 50-50 chance of getting it right. Either the reaction does represent the formation of 1 mole of compound from the elements, has to be elements, not other compounds, and the elements have to be in their standard states and their standard conditions. If that's the case, then their delta H of reaction is a heat of formation. If some of those criteria aren't met, then their heat of reaction is great, it's just not a heat of formation. So, Benny, I guess you don't have the answers to these. So what do you think, Benny? Formation, this is methane over here, CH4.
I think it's the heat of formation.
She does. I agree, and I can make this a game. Does anyone want to challenge Benny? But no, she is totally right. She did the check. It's the formation of 1 mole of methane, and that these are in their elemental form. Not only are they in their elemental form, but they are in their standard state and standard conditions. And you're like, well, hydrogen, how would I know it's a gas? Well, just think of hydrogen. Is it a gas? Yes. If that would have been hydrogen solid, that would have thrown it out. And it would have a different heat of reaction. Okay, going back to you, Allison. What about this one? No, and tell me why.
Well, there's a solid, a gas, and then
That solid though, what you know, maybe you might not know, but lead, when you, whatever comes to mind, like a picture of lead, would it be solid at 77 Fahrenheit and high pressure? Would it be solid? Mm-hmm. Lead is solid. I know, you're like, how do I, let's see, how do I think of lead? I don't know, like I'm trying to think like a fishing weight. I don't know if they used to make them out of lead. Probably they don't because of environmental concerns. But lead is a solid. So now, Allison, if I say that lead is a solid at normal temperature, 77 Fahrenheit, and 1 bar pressure, now what would you say? Yes. You would say yes. I would too. So with that in mind, lead is in its standard state. Chlorine gas is in its standard state, and actually, I didn't say anything about the product, but then we have 1 mole formation of product. Yes. So, yep. Very good. All right. Logan.
No.
Why?
Because PCl is in the liquid state.
Because PCl3 is in the liquid state?
Yeah.
It's not, but that's not why.
Is it PCl in its gaseous state?
It has to do with
PCl5.
PC. It does. No. No.
I don't know though. I'm not sure.
It does fail. Does anyone else know why it fails?
Because it is a compound.
Yep. Because you can't make it from a compound. It has to be elements. Very good. Yep. Tricky. So yeah, it fails because of the PCl3, but it's because that is actually a compound and not another element. Good job. Do I only have 4 of these? Maybe I only have 4.
She can go if she wants now.
We might pick on you later, so hold that thought.
Well, how about yes and no? I'm just kidding.
Okay.
Okay, so I want to say yes because there's element and then an element and that makes a compound, but I'm really not sure. Like SR, what is that?
Strontium.
That sounds like it would be metal or something.
Yeah, it sounds
So
like it would be solid.
So yes.
What if I told you it fails 1 criteria?
Then I would ask you, please explain because I'm confused.
And what if I were to circle? Yep.
Could you expand a little bit?
Yes, I will. I think I heard Benny say, so standard molar enthalpy of formation, it can only be 1 mole. It can only be one.
Yeah.
I know, you're like, really? That's picky. Ah, drat. So, name Madison. Madison, I have a follow-up question for you. So do you see why this isn't this fails, we can't put an F there because that's 2 moles of formation. But Madison, how could we clean it up so we can get just 1 mole of SRO formed? If we go from divide it, exactly. And we divide this by 2, this by 2. Oops, sorry, you know what I mean. This by 2, and then this by 2, and then your enthalpy will be an enthalpy of formation. That's actually been kind of a test question. Does that make sense? All right, cool. So these are some. Oh yeah, okay. It's like basically it's a continuous table that's been kind of wrapped around. So these are some substances, and these would be the delta H naught sub Fs. Delta H naught sub Fs. Standard molar enthalpies of formation of these things. We're going to pick on actually, which one are we picking on? I think it's this one. I think we're picking on methanol here in a minute, so I'll go ahead and circle it. This guy right here. So we could take any of these and put it as the product, and then go ahead and just kind of tack on elements as reactants, and make a little equation showing the formation of these. Okay, and that would be the heat of the reaction. These are in your OpenStax textbook. In the back, one of the appendix G, actually has some values. Yeah. Now, these guys, this is the column we're covering now. Delta H's. Delta H sub, I don't know. They're standard molar enthalpies of formation. I'm not sure why it's the subscript 1. These other two, this is actually, the G is Gibbs free energy, and my favorite is the S is entropy. We won't get to those until Gen Chem 2. Collectively, those 3 columns, what they have in common is those are thermodynamic constants or values associated with those compounds. Appendix G continues, and it's broken out by element in case you have to kind of leaf through those. So we have carbon here. These are all carbon-containing compounds or elements. And this first column is what we would be looking at, standard molar enthalpy of formation. Notice some are endothermic, like CO2, and some are exothermic. So why, oh, well, anyway, I'll just go ahead and answer my own question. Check this out. Carbon. You're like, why would I have carbon 3 times? Well, I have carbon, solid graphite. What do we say about that? That is the standard state. It's 77 Fahrenheit, 1 bar pressure. That means the standard molar enthalpy of formation is 0. Carbon could be a diamond. Okay, carbon in its gaseous state. Okay, so it's not in a standard state, then it's not going to be 0. Then we have chromium, so it's just alphabetical. So it's kind of clustered, so that's Appendix G. Every once in a while, I will tell you that I'll be working a problem for this class, and instead of finding an OpenStax textbook like I should, I just Google it. Like, what is the standard molar enthalpy of formation of methanol, you know, in its liquid state? I'm not saying it's what I should do, I'm just saying it's what I do. Okay, so it continues like that. So let's work a problem. Oh, I told you methanol, but actually it's ethanol. So a few slides ago, was this one on there too? C2H5OH? Here. Okay, a few slides ago on the table.
Yeah.
Okay, good. And it's so small. Oh my gosh. There, is it there? Thank you. Yep, negative 277.7. Yep. So we're going to focus on that one. We're going to basically take it apart. That's going to be our product, and we're going to write the form. We're going to have a carbon, a hydrogen, and an oxygen. So here we go. Carbon. So I don't know. How do I say this? I'm just counting on you knowing some of these things because we've talked about carbon enough. The standard state is going to be in its graphite allotropic phase. Right? Hydrogen, gas. Oxygen, gas. Okay? So I'm counting on that at this point. So those are going to be our reactants. So to write it, it looks like this. I would start with what I want to produce. So this is my goal over here, my C2H5OH. As I was going through my notes today, I'll tell on myself, I was like, let's see, how many, we only have 5 hydrogens over here in 1 mole. No, we don't. We actually have 6 hydrogens. And the reason it's written like this, as some of you maybe know, is I want to emphasize, or we want to emphasize that OH is a hydroxyl group, yes. All right, so all we got to do is go over here, write our reactants, and I kind of said what they're looking like over here. So we have 3 reactants, and I wrote them in this order: carbon, solid, graphite, hydrogen, G for gas, oxygen, a G for gas. And kind of like I threw on Daniel and Madison, we definitely need to keep this as a 1 mole, standard molar, 1 mole, molar enthalpy of formation. Then we have to go back and clean up. So Benny, what is the stoichiometric coefficient going to go in front of the carbon? 2, I agree. So Allison, what stoichiometric coefficient are we going to put in front of the hydrogen? A 3, exactly, to get 6, very good. And then Logan, what are we gonna put in front of the O2?
1/2.
1/2, perfect. 2, 3, 1/2, great. So that's it. So I think on the next slide it says,
What is the DH of the reaction?
what's that?
The DH of the reaction. That was just,
It's the negative 277.
okay.
Yeah. What did I do? Part 8. I must put that in the wrong spot. So I'll put all this up here and I think this is what maybe you were saying, Benny. The heat of that reaction, it's what? Exothermic, because it's got a negative delta H. And specifically, it's negative 277.6 kilojoules. So 277.6 kilojoules of energy would be released by taking 2 moles of carbon, 3 moles of hydrogen, 1/2 mole of O2 to produce 1 mole of, I get my methanol and ethanol mixed up, ethanol. And not so surprising, it coincides with a few slides ago what the enthalpy of formation of C2H5OH is. And it should. So, hope that makes sense. So this is enthalpy of formation.
So, wait, how did you get the DH of the reaction?
So that would have to be given to you.
Oh, okay.
Yeah. That's a good question. I thought that was like, that came out of thin air. Somebody experimented and gave us that. Yeah, that's a good question. We didn't have any data to go on. I guess though, if we knew that we had created a reaction that represented the standard molar enthalpy formation of a compound, we could say, I know what that is because I know what this is. So I think that's kind of the point. Very good. All right. Well, that's one way to come up with the standard molar enthalpy of formation from a table. But what we run into is, if I look on the reactant side here, I have reactants, reaction arrow, products. So if I look at my reactants, and if they aren't elements, okay, in their standard state, then I'm going to go this route. So what this route is something that we're going to do other times in chemistry. The large Greek letter that looks like an E, that means summation. So that means summation. And I think we ran into it when we did the average atomic weights summation. And so that means you add together, sum means you add, for every product you have. If you read this, I'm going to take the stoichiometric coefficient of that product. I'm going to look up their standard molar, I'm going to write the name table here. I'm going to look up their standard molar enthalpy of formation on the table, multiply it by their stoic coefficient. It's easier to show you what this looks like. It sounds complicated, but it's not. For every product, I'm going to take their stoichiometric coefficient from the balanced equation, multiply what I get from the table, that's the standard molar enthalpy of formation. I'm going to add those together. Now, this product, summation of products, and I'm going to do that for the reactants. We're going to do a problem here in a minute. I'm going to do that for reactants. And I really suggest strongly that you do a little paragraph up here for the products, a little paragraph here for the reactants, and then notice what we're going to do. We're going to subtract. Okay? I would do it that way. And then subtract. It's nice and neat. No one gets hurt. Well, I started to say, oh, our deltas are always, it's the change in, it's always final minus initial. And actually, this is consistent with that. What are the products? They're the final. What are the reactants? Okay, they're the initial. So I like it when things kind of come full circle. All right, so like I said, it's easier to show you than it is to kind of describe it. So we're going to pick on this one. Now notice that this is, this is an example talking about magnetism today. I didn't plug it in, but I described what it would do. Okay, so anyway, I don't like electricity either. I don't like fire, I like electricity. So we have two reactants, but notice that one of the reactants is a compound. So you're like, oh, this can't be a standard molar enthalpy of formation. No way, no way. But I do have the standard molar enthalpies of formations of both of the reactants and both of the products. So I can knock out the heat of this reaction, the delta H of the RxN of that whole thing, okay, using their individual standard molar enthalpies of formation. So in other words, this is this up here. I'm going for the heat of this reaction under standard conditions. And not to be confused, the first two things listed here are the reactants. I'll put an R there for the reactants. The next two things listed are the products. Okay, just to kind of get our bearings. This information came from the table. And we kind of have a star child here. O2, since oxygen is a diatomic element, oxygen under 77 degrees Fahrenheit in 1 atmosphere, basically, it wants to be diatomic in its gaseous state. So it's in the standard state, or standard conditions, so its standard molar enthalpy formation is 0. We would see that on the table. All right. So on the next couple slides, what you're going to see is I'm going to focus on the products first. I'm going to focus on these two guys. And I am going to take their stoichiometric coefficients. Their stoichiometric coefficients of 6 and 3. And I'm going to take this number times 6 and this number times 3. Why? Because that's their stoichiometric coefficients. I'm going to come up with a number. And then for the reactant side, I'm going to take my C6H6 times 1 and my O2 times 15 halves, which anything times 0, of course, is 0. But that's kind of the deal of it. I hesitate to even show you that because I'm just kind of trying to emphasize what rolling out the problem is going to be. Don't do it like that. Do it like this. I mentioned the two paragraphs. So I would actually start by saying the summation of A, and A is the variable representing the stoichiometric coefficients. The summation of each of the products looks like this. For the CO2 term, the stoichiometric coefficient was 6, which means 6 moles of CO2. And then from the table, the standard molar enthalpy of formation of CO2 is negative 393.5 kilojoules of energy for 1 mole of CO2. Now, the summation part means I need to add. In this case, I'm going to add two terms. I need a term for the H2O. There were 3. The stoichiometric coefficient in front of H2O is 3. So we have 3 moles of H2O times its standard molar enthalpy of formation, which is negative 241.8 kilojoules of energy per 1 mole of O2. So we have a deal where we're multiplying within the individual terms, and then we're going to add them together. So my thing is most likely, but the 6 and the 3 are exact, so I'm going to go with 1 decimal. Bottom line is on the product side, we have negative 3,086.4 kilojoules of energy. So, did I say I would like to see it organized? I did say that. I'd like to see homework, and you're going to have one of these on your next test, which is a week from Thursday. I promise. So stay organized. All right. That's the product side. Let's look at the reactant side. Again, we have 2 reactants. So for the benzene term, the stoichiometric coefficient was 1. So we have 1 mole of C6H6. And if you're like me, sometimes I'll put a little plus there. Sometimes I do, sometimes I don't. But no plus or minus means plus. But its standard molar enthalpy of formation is that 49.0 kilojoules per 1 mole of C6H6. The oxygen term, a lot of times students, again, since O2 gaseous is its standard state, It's 0. Standard molar enthalpy of formation is 0. Sometimes students blow that off. Don't blow that off. Or I'm going to take, if the problems were 10 points, I'm going to take off 9. Don't blow it off. The 15 halves came from a stoichiometric coefficient. So I can do that math, can't you? Right, we're looking at 49.0 kilojoules of energy on the reactant side. So here's where I said stay organized. Sometimes students like to just string it all up. I wouldn't, because it's easy to get your sign wrong. Because now we're going to take the product minus the reactant, so it looks like this. So it's that negative 3,086.4 kilojoules minus a positive. So negative or minus 49.0 kilojoules of energy. So that makes even a more negative number, doesn't it? So you get negative 3,135.4 kilojoules of energy would be the heat of that reaction. That would be the delta H sub Rxn for that reaction. What was that? The combustion? Yeah. Very exothermic? Yep. If this is one where you're like, Mrs. Snipes, remember when you did the delta T's and your Celsius temperatures had the same units and you just put the degrees Celsius outside your parentheses? You could do that here too, because we're doing temperatures.
And can we just put kilojoule just in the result? Like,
no, you have to have kilojoules in your as you work it. But what you could do is you could have negative 3086.4 minus 49.0 and then put a kilojoules outside. Yeah, you could do that. All right. Very good. A few slides, like, I don't know, 5 slides ago was my part 8, and I was like, what? So anyway, here we go. We're going to do a little bit of part 8. Get us down the road so we can finish knocking her out Friday. Okay. But part 8 continues with thermodynamics, checking where the thermal energy is released, where thermal energy is absorbed. Okay, it's kind of fun. It's the icing on the cake. Not sure why that's showing down there, but just ignore everything down there. So this statement actually is a general statement that can go for a couple of different ways. And it makes sense. And I kind of tease sometimes, like if I have kids that come to your houses or trick or treat, and they have like, this is my sword, like my magical sword. So if you have a sword, we can use that sword to break bonds. So if I have an H2O molecule, I go, okay, so I can break the bond between the oxygen and the 2 hydrogens. And it takes that energy, okay? And we'll talk more about this later in Gen Chem 2 maybe, but as those are chemical bonds, as chemical bonds are formed, if I had a sword there, it would energize my sword. As those bonds are formed, energy is released. It takes energy to break bonds. But today, or in Chem 1, what I want to talk about are the intermolecular bonds, the bonds that connect the material. So to kind of remind you how that works, I'll bring up this little animation, hopefully. Liquid gas, the 3 physical phases of matter. And as you go from a solid to a liquid, you're breaking those bonds. As you go from a liquid to a gas, you're also breaking those bonds, okay? And that's going to require energy. So those would be endothermic processes. I have a slide coming up, but you guys know that if we're going from a solid to a liquid, we call that melting. A liquid to a gas, we call that evaporation. Okay. Now, if we go back the other way, and as I have them listed up here, that would be from right back to left again. If something goes from a gas to a liquid, like in clouds and such, we call that condensation. Okay. If something goes from a liquid to a solid, we call that freezing or solidification. In those cases, it's becoming more ordered, which is a whole other thing in physical science, but it's becoming more ordered, more bonds are being formed, and as bonds are formed, energy is released. So as you picture those processes, you're going to almost have to picture a squiggle out with regard to energy. So I have some of the table that I showed you clear back in Unit 1. Looks like this. With regard to a solid, it's stuck within, it has a definite volume and a definite shape. It's not budging because it's rigid, right? High degree of intermolecular bonding, a low amount of kinetic energy. If we go to a liquid, it's kind of in between. If we go to a gas, oh my gosh. A gas takes on the volume and the shape of its container. So its volume and shape are indefinite. Basically, zero connection to other gas particles and a lot of kinetic energy, a lot of motion. All right. So phase changes, like I said, you guys know these. You learn them, I don't want to say in kindergarten, but something goes from a solid to a liquid, we call that melting. Something goes from a liquid to a gas, we call that evaporating or vaporization. So those would be endothermic. Endothermic. Something goes from a liquid to a solid, we call that freezing. Something goes from, what I do now, gas to a liquid, we call that condensation. These would be exothermic. So endo, just to make sure we're all on the same page, those are going to be, here actually we're going to have to pick up, we're getting close to having to pick up here on Friday. There actually is going to be a delta H associated with those, and they are going to be, let's see, endo, they're going to be positive, so they're going to be greater than 0. And these guys, their delta H's associated with those processes are going to be negative, so less than 0, and they'll be negative. Well, I think that's a good place to stop. We do have, I think we'll get through it Friday. But, so I have a couple videos coming up. Hopefully we'll figure out how to make them play. All right, and tomorrow we're doing the lab with enthalpy of solution, heats of reaction. I can't remember what the title is. But we're using the calorimeters again, and so it should be kind of short. I hope you're not disappointed.